So let's start series. So again, to kind of give an overarching idea of what this unit is, we are going to be trying to answer the question, if I add up a bunch of numbers, do I get a number or do I not get a number? That is, yeah. No, this is definitely new. We are firmly in the C. Oh, cool. This is firmly in the C part of calculus. So this is all new. And honestly, we're probably not going to take a derivative or an integral until 8.4. So, wow. Yeah.
How do they determine what's calculus A, B?
So I'm not really sure why they name it like that, because in college it's Calc 1 and Calc 2. In my mind, A is derivatives, B is integrals, C is the rest. Mostly series.
Is Calc 1 equivalent to AB?
Mm-hmm. Calc 2, BC.
It works.
You're not.
I said I would be the equivalent to Calc 2. He's like, no, you're not.
Yeah, you are. College kids think they know everything. Yeah. Kind of. If C is like a real thing, yeah. All right, so I'm going to start going over some of the basics of series. We're going to get a little bit wishy-washy today for like the first half, and then we'll get a little more concrete. Geometric series in general, very important type of series, but let's just talk about what a series is. Has anyone seen this notation ever before? Yeah. All right, so you've probably seen this in Algebra 2. Maybe you talked about some types of series. In pre-cal, theoretically, you talked about some type of series. One thing that's going to be different than Algebra 2 for us, maybe similar to some of the ones you've done in pre-cal, is this thing at the top. We are always going to be talking about infinite series pretty much. So we're talking about not one term, not 10 terms, not 100 terms. We're talking infinitely many terms. And infinity makes things weird, which is why some of this stuff will be a little bit mentally challenging. Now, there's a difference between sequences and series. A sequence, which we're not going to talk about too much, is just a list of numbers. So I could do 1, 2, 3, 4, 5. The Fibonacci sequence, 1, 1, 2, 3, 5, 8, where I add those terms together. A series, we're going to add them. So this would be like a sub 1 plus a sub 2 plus a sub 3. If we want, we can skip some stuff by putting an ellipse in there, ellipsis, whatever you want to call it. But we will have a plus dot, dot, dot at the end. Now you're going to see me write a lot of series like this, where it's the first 3 terms, I give some space and give what's called an nth term. This nth term is like a rule for the series. So think of it like your f of x equals whatever. It's like a function. But a series, you're only plugging in specific things. You're plugging in 1, 2, 3. So I don't like have a sub 1/2 ever. I don't like have a half term. This is where my series starts. This is the Greek letters, sigma, if you care, uppercase version. So sometimes you'll hear that notation called sigma notation. That's just talking about the letter. And if I put a number up here, this is where our series ends. For us, it won't. We're going to avoid using this notation when we can because it gets a little bit finicky. You'll see a lot in this unit, but in our next unit, that's going to be about a specific type of series called Taylor series and power series. We'll often write them out in this notation where we list the first 3 terms in the general term. A lot of argument happens over where series start. So let's talk a little bit about some series that you may have seen before, specifically arithmetic, and then we're going to focus most of our time on geometric. One way to figure out if a series converges or diverges is to take what are called some partial sums. So if I add up the first term, the first and the second, the first and second and the third, and I kind of see if that sequence looks like it's going to a specific number. So we're going to do the first couple of, well, I'm going to do the first couple partial sums, and then I'm going to have you guys kind of look at this. So here's our nth term. Here's how we find each number in the sequence. So in the series. I'm going to mix those 2 words up, and it's going to be frustrating, and I apologize. So our first term is 3 because I would plug in 1. 2 times 1 is 2 plus 1 is 3. This one I would plug in 2. 4 plus 1 is 5. 6 plus 1 is 7. So that's how I'm getting those terms.
Oh, you put one in first.
Mm-hmm. So first term, second term, third term. This is always where we start. You're good.
Oh,
I'm glad you think so. All right, so let's find what. Yeah, so you remember this a little, and this one's called an arithmetic sum. So what's the? How do I get from 3 to 5 to 7 to the next one's 9 to 11 to 13? Arithmetic. Arithmetic. What do you add specifically? You add 2 every time. So an arithmetic sequence is when there's something called a common difference. And you talked a lot about arithmetic sequences. If you remember in Algebra 2, I know it's a long time ago. So what I want to do is talk about the sequence of partial sums. So I'm going to find S sub 1, and I'll probably go up to 3 because you'll see the pattern by then. And then I'm going to ask you to find S sub 4 and S sub 5. What I mean by partial sum is I'm going to add up that many terms of the series. So S sub 1, I'm adding up the first term, it's 3. Wow. The next term, I'm adding up 3 plus 5. I get 8. Next one, 3 plus 5 plus 7. And I get 8 plus 7 is 15. Will you quickly find for me, using your noggin or a calculator, find S sub 4 and S sub 5? Why is Mountain Dew the best?
Yes.
The blue one?
Any of the blue ones? Any of the blue ones?
Did you hear about the one they made for like Christmas time this year? That was like it was white, and it was eggnog flavored. Or wait, no, gingerbread. Either way, it sounded disgusting. Ooh, I saw the commercial for that one. It sounds good. I've had it before. It reminds me of a slushie I used to have when I was a kid.
Whenever I have it outside of school, it reminds me
All right, sounds like Nick's got it. So do we like 24 and 35 for the next ones? Okay. So one way I can try to find if the infinite series converges or diverges is to look at what would be called a sequence of partial sums. I know I'm throwing a lot of like big words out today, but they all make a good amount of sense when we talk about them. So what a sequence of partial sums would be looking at this set of numbers as a list. So 3, 8, 15, 24, 35, and I could keep going. Notice I don't have the pluses in there. This is just a list of numbers. That's what sequence means. Now, does that look like the sequence is going to have a place where it ends up? Does it look like if I took a limit, if I had a rule for that, or if I looked at where these numbers go eventually, does it look like they're approaching a specific place, a specific number? It looks like they're getting bigger forever, right? So if I had to write this down, it looks like the limit as n approaches infinity of our partial sums is infinity. So what do you think about this, this type of series here? Do you think it will converge or do you think it will diverge? It diverges. So this means right here that our series diverges. Now, so what that means for me is if I'm adding up infinitely many numbers here, I take 3 plus 5 plus 7 plus 9 plus 11. If I add all of those up, I'm not going to get a finite number. I'm going to get something that's too big. Exactly. Exactly. Kind of. So let me see if I can make one real quick. So the things we're adding together, let me see if I can find something. Do I have something already? So this unit does get a little bit hard to visualize. Oh, I thought I had made something. Darn. All right. I might have to pause and come back to that visualize. Because we're kind of adding very discrete numbers. So if I made a graph here, what that graph would look like is more like dots going up, and we're adding specific numbers because we only have these plug in 1, plug in 2, plug in 3, plug in 4. So it's not really like a continuous graph like we would think of. It's like a very specific set of numbers. But mostly the question you're asking is, if I add all these numbers up, 3 plus 5 plus 7 plus 9 plus 11, and I keep going with that pattern, will I get a number? The answer is no, because I'm always going to be adding something positive. That positive thing is always getting bigger. Yeah.
So what if you after you say that it's 5 versions and it has a vertical asymptote, like it converges like the horizontal asymptote?
Kind of graphically ish. More than a vertical asymptote, you're thinking like end behavior that just goes up or down forever. So instead of like asymptotic, kind of. All right. So my question becomes then, arithmetic series, I either add something every time or I subtract something every time, and that something is the same. So notice for each term here, I added 2 every time. I could also subtract 2. So I could have done like 3 plus -1, that's subtracting 4. 3 plus 1 plus -1 plus -3 plus -5 plus -7. I could do that as well. Do you think that any of those will actually ever converge? So we could have functions that oscillate. That's going to be called alternating. That might help a little bit, but it depends. But with this arithmetic series, we're actually never going to converge. So these will never converge. So we're actually going to stop talking about them literally right now. You spend a lot of time in Algebra 2 talking about them because there's cool ways to write formulas and stuff. But these are never going to converge because I'm always either adding something positive and those terms are getting bigger and bigger and bigger. So I'm going to push those terms. I'm going to add something positive every single time, or my terms are going to get bigger and bigger and bigger in the negative direction. And I'll be adding like -7 plus -9 plus -11 plus -13. That's going to go straight down to negative infinity. So what we're going to talk about for the rest of today are geometric series. These are much more interesting because there's going to be very specific ways that we can tell if they're going to converge and diverge. All right. Can anyone figure out, here is a geometric series. Looks different, yes. What does it look like is happening between each of the terms? Denominators are getting bigger. I heard times. What am I multiplying by each time? Times 2 on the bottom. So each one of these fractions, I'm multiplying by 1/2, right? This is what's called a common ratio. You might have heard of that. Really, we're going to talk about the word ratio a lot. That would be what I multiply by each term to get the next term. And the way we're going to decide if something converges or diverges, we're going to end up looking at that number. So again, I want to find some partial sums, and I want to do this with decimals because I want, like last time, to see if we can find a pattern for that limit of the partial sums there. So again, I will show you what I want for S sub 1 and S sub 2. I'm going to ask you to do a lot of them. We're going to go all the way out to 10. Now, this would be great if I had a formula for these partial sums. It actually turns out to be pretty difficult to find a formula for the summation of it. So we won't do that very often. Here we're kind of seeing if we appear to see any patterns. Is there any kind of apparent pattern? So our first term would be 3/2, but instead of writing that, I'm going to write 1.5 because it's a lot easier to see patterns when I'm looking at decimals. Limits are a little bit harder to work with if I'm looking at fractions. For the next one, I'm going to do 3/2 plus 3/4, and I'm going to use Desmos if I can find where I put it. You're going to use your calculator. And I'm going to do, again, I'm going to use the decimals, so 2.25. If you want to be lazy, just take whatever answer you did and add 3/8, not on your OneNote, ideally on your calculator. All right, 2.625. Now you're going to have a lot more decimals as you go. If you want to round to 3 or truncate at 3, that's perfectly fine. I'm going to give you a couple of minutes to try to finish out all the way through the partial sum S sub 10. And then I want you to see, can you make a conclusion? What does it appear to do? Where does that list of partial sums appear to go? You might not be completely convinced, but it's going to appear to approach somehow. There isn't one. No. I mean 89. All right, so you're getting the rest of those partial sums and seeing if you can make a conclusion. Do you think your sequence of partial sums, your list of partial sums, is approaching a specific number? If you want kind of the graphical comparison, I kind of like options where it's the best. You're thinking, if I listed out these numbers and looked at them graphically, you're kind of thinking about horizontal axes. Are they approaching a specific place? Let's take this trig off the board. All right, I'm going to start to catch up since I wrote these out earlier. All right. Are your partial sums kind of similar to mine? Not even close. Way to own that, though. I like it. What did you do?
I was more playing with two.
That was common ratio. Would you like a pencil? They're over there. I got a whole mug of them. Okay. Have you thought of erasable pens? They exist. Okay. That's fair. That's fair. Yeah, Jill. I was just doing that here because we're just kind of looking for a pattern. So we're being a little wishy-washy about this. So if you have them rounded differently or truncated, whatever, as long as we're close to this is fine. The whole point of this, we probably won't do this in the future, because listing out these terms, am I actually proving that this approaches a specific value? No, I'm just using a pattern to kind of make some conclusions. They might not be completely true, but what do these numbers appear to approach? 3. And I will tell you, they do actually approach 3. I haven't proven it because they could be approaching 2.998, and I wouldn't know just by doing these ones. If I could take all of the time in the world and actually go out to infinity to do this, I could prove it, but that you can't actually get there. Yeah. An integral test would be a great option. You're like 4 sections ahead of me. Yeah. So we're going to learn different ways to prove them. An integral is definitely one of them. We're going to be comparing to a similar integral. It's a little bit different because we're adding very discrete values up instead of like a whole function, but that is a good comparison. So this appears to approach 3. So do you think this series, this geometric series, do you think this guy converges or diverges? converges. All right. And what do you think the sum is? Where did we converge to? 3. So what that's saying is if I add all of these infinitely many numbers up, I get 3. There's actually a really, really funny, being a relative term, joke that mathematicians like to tell. Well, scandalous because it involves a bar. But infinite number of mathematicians walk into a bar. First one asks for a beer. The second one asks for half a beer. The third one asks for a quarter of the beer. The next one asks for an eighth of a beer. And the bartender says, stop, pours 2 beers, and walks away. That's a geometric series that converges to 2. So here, first mathematician asks for 3 halves of a beer, 3 quarters of a beer, 3 eighths of a soda, and and they say stop. They pour 3, and they're like, just share it. So we're going to figure out a way to actually confirm that that is 3. But what do you think about these terms helped it to converge? Why did this set of terms, when I added it together, give me a number, whereas this set of terms got me something too big to be a number? What helped me in this situation? All right, the number on the bottom is getting bigger, so the successive terms were getting smaller and smaller and smaller. So what this is going to do, what do you think about other geometric series? So the only qualification for a geometric series is that I need to take one term and get to the next one. I multiply by a consistent number. Do you think all geometric series will converge? No? Why not? The common ratio could be like 5. What if my terms were 1, 5, 25, 125, 625? That's all the powers of 5 I know. That would get really, really big, really, really fast. So some of these will, but it's going to depend on that ratio. All right. One of the big things we're going to learn towards the end of actually our next unit, the end of Taylor series, is something called Lagrange bound for error. It is the probably hardest thing we learn this year. So any opportunity I have to talk about error, I'm going to take it so we have an idea of what that looks like before we get there. So our error in our approximation is just the straight up difference between the actual sum and the sum of the terms that I've added. You can compare that to, like, in a science class, you might talk about percent error. We're going to take the percent part out of it. We just want to know how far are we from our actual approximation. So if we did our approximation, our actual sum, which is S without any subscript, minus S sub 10, our error for that term would just be 3 minus our 2.997. We'd get 0.00. No. Sorry, abs bars. How do you think I could make my approximation like better? How do you think I could make my error smaller? Yeah, Connor. Yeah, more terms. Yeah, the problem is we don't want to keep going forever. So when we make approximations, we're going to stop somewhere, and the where depends on how you want to be. All right, so let's go back to the idea that some of these geometric series might diverge. Will you, for me? I want us to just find S sub 1 through S sub 5. And by us, I mean you guys. So will you find the first 5 partial sums, and then tell me what you think the limit of those partial sums is? If you want, also consider what do you think R is as we go. So give me S sub 1, 2, 3, 4, 5. Where do you think the limit goes? Bonus point. What is R? Am I actually going to get all the notes done I want and give you half an hour to work on your problem set? Is today magic? It's because we're starting series.
Okay.
I keep thinking it's a day later than it is. So it feels like Thursday.
Okay.
Sorry.
Are you gonna make a math test on Friday?
Do you want to?
No.
No, because I don't want to make that down.
We meet on Mondays and then we.
Oh, you work here?
No.
The test is going to be partner test, and on the day it does know activity, you're going to plug in the answer, and if it's right, you're like,
That's cute.
what? Happy partners. So my other book, I'll probably still do relatively close grades because that makes for better conversations, but I'll mix them up so that I think you're working. What? Need to mix that up.
Put my grades right in.
No,
I'm gonna let my partner down.
Lily, you're not gonna let anything laugh down.
Yeah, no, I'm gonna let them down.
Believe in yourself.
How are you guys not walking over there?
Don't know where he going.
And be like,
All y'all are wrong. I am right. Prove me wrong. I've only had one other female student do that. I actually did a fun social, I'll tell you later. Fun social experiment where at the end of the year, I gave them a bunch of assignments, but everything was mastery. So they had to give their own grades. At the end, they had to like pitch me their grade. Every boy student said, I deserve 100. Everyone. All the girls said, well, I think I deserve somewhere between a 92 and a 95 because I worked really hard and I got all the problems right, but I didn't get them right on the first try. Every single one. It was the weirdest social experiment ever. So weird. And they didn't even like give me a number. They gave me like a range. So they were like, here's what I think I should get, but like you can choose. I was like, so I had one girl student who walked in and she thought she was right all the time. And she was my favorite. Her name was Drusilla. She's great. Yeah, she sat right there. Power. All right, let me see if I got some of these partial sums right. 1.5, 3.75, 7.12, 12.188, 19.71. We got something like that? All right, if you had to tell me where you think they're going. Yeah, so do you think this series is going to converge or diverge? All right, so these are not super rigorous proofs. So we're getting closer to having an idea of what this proof is going to look like. Here we're kind of investigating. We're making some predictions. So we're about to transfer between predictions and how do I rigorously prove this? And that has to do with the R. Did anyone think they had a good number for Nicole? What did you get for R? 3 halves. Do you agree with Nicole that every single time to get from one term to the next, you multiply by 3 halves? Yes? Does anyone else see 3 halves anywhere? Yeah, does everyone see right here the thing to the n power? That makes sense because if I put another exponent on, that's just adding another multiple of 3 halves. That's going to be super helpful. This one actually works the same way since this is the only guy to the n power that's the 1/2 there. We're going to be better at picking those out in a second. So I'm about to write down some rules. But I want you to predict first because I think you'll be able to figure it out. So you don't have to write it down yet, especially if you're James and you're writing in pen and you're scared. Based on the R. So I'm going to write something in here and something in here. It's going to have to do with the ratio R. When do you think, based on the R, this is going to converge? When do you think, based on the R, it's going to diverge? I want you to think about it for a second. So if you think you know, talk to a neighbor. And by a second, I mean like a full minute. So when do you think it will converge? When do you think it will diverge? Peek back in your memory. See if you remember the sum. You're going to be so good at this unit. I'm so excited.
Same thing, it'll just work itself out to negative.
Also,
If it is one, then it doesn't change, it's the same thing.
So you're saying the term will be the same?
Yeah,
So what if I did one?
and then you add, that would have frozen it. Because one. If it's a negative, a negative, but it'll still be a negative number.
All right, let's get some of these ideas down. Does anyone want to tell me some of their thinking? When do we think this series is going to diverge? Cora, what do you think? All right, so if our ratio is greater than 1, I would agree. I left some space around it for a reason. Sushan, you got anything to add? Good. Perfect. All right, so we've got a lot going on here that Sushan just added. We'll talk about it in a second, but I want to put, would you guys agree, converge if the ratio absolute value would be less than 1? Okay, so what that's going to do is it's going to make the terms smaller every time. Which is good. We want those terms to get smaller as they go, because eventually we want to think of like if I made it to infinity, I'd want to be adding nothing. So I need my terms to get closer and closer and closer to 0. Now let's talk about the equals to 1. What would the ratio being equal to 1, what would that do to our terms? Let's say our first term was 1 and my ratio was 1. What's the next term? What's the next term? How many terms am I adding? Infinitely many, right? So what's 1 plus 1 plus 1 plus 1 plus 1? If I go all the way out to infinity, big, right? Infinitely many ones is infinity. So that's why that equal to is on the diverges. Again, the absolute value bar is just taking care if our ratio is negative. Kind of going back to what Austin said about oscillating, our terms can what's called alternate between positive and negative. So I could have like 1 minus a half plus a fourth minus an eighth plus powers of 2. You know what I mean. Thank you. So those can happen. Now, I'm going to write down a formula for the sum of a geometric series. This is the big thing that you might remember from Algebra 2. If you don't, it's not hard to memorize. But this is the one thing that I'm kind of bringing back that you might know. It's the thing I told you yesterday. It is A over 1 minus R. Does that look familiar at all? Okay. If it doesn't, it's no big deal. We're just going to learn it now. So the formula to find the sum, I'm going to write it up here as well, but I'm going to translate it because I actually think they do a disservice in Algebra 2 with talking about what these things are. So you can kind of see we've got some different formats for what this geometric series will look like. We're usually going to deal with this first one. Kind of a weird thing. Usually our geometric series will start at n equals 0. And that's because it'll put to the 0 power here on the R. So that A is actually not just the A right there. It's whatever our first term is. So if you plug in whatever that index is on the bottom, the n equals whatever. If I plug that number in, that's my first term. That's what goes on the top. What do you guys think the R is? The ratio. All right, things that have to be true for this to give me an answer. I do need a number of infinite terms. So I couldn't have like at the top of that sigma notation, I couldn't have like 5. I can't add up the first 5 terms this way. I couldn't use this to find the sum of those partial sums I was doing. So this has to be for the infinite terms. And to use that formula, our series has to converge. So our absolute value of R has to be less than 1. The series has to converge. So when we're thinking of converge, diverge here, kind of the same thing with a number versus infinity. For something to converge or for something to have a sum, those are the same thing. So if I have a sum, my series converges. If I don't have a sum, usually meaning it's too big, my series diverges. All right, so basically all we've done today was like investigation. So these next two questions are like the ones that I'm actually going to ask you to do. So I want to show you how we're going to construct the argument when we get to a problem set, when we get to a quiz, when we get to a test. All three of those we're going to do for this unit. We're actually going to have a quiz. It's been a while. I know, right? Probably going to have a partner quiz. We're just partnering it up. What? We had one in unit 1. Wow. All right. So I would say all of what we've been doing so far is to get ourselves comfortable with what a series is, what a geometric series is. These are the types of questions that I would actually ask you to do. As we do these questions, I want you to pay very close attention to how I'm writing things down, what I'm writing down. The answer of converges or diverges is not very cool. What I am grading when I look at these is an argument. Pretend, whatever profession you want to pretend you are, a lawyer constructing an argument, a doctor constructing a treatment plan. That's a weird analogy. A mathematician constructing a proof. That's what you're doing. So it's going to be a little more writing than we think. So first things first. I'm going to rewrite this one to make it look a little bit more like a geometric series. When I say that, usually we have a number times our ratio in parentheses to our n power. How I'm going to do that, I'm going to pull this 3 out front. And I'm going to keep that 2 on the bottom. What could I put on the top that's not going to change this? A 1. So these two are equivalent. And now that looks more to me like a geometric series where I see a number times a fraction to our n power. All right. To make our proof, we're going to first identify what we think R is. What do you guys think R is? 1/2. It's that thing to the nth power if I'm using my sigma notation. Again, that common ratio. Keep in mind, as I'm plugging in bigger and bigger forms of n, I'm multiplying by more and more 1/2. All right. Why do I care that the number is 1/2? The reason I care is the absolute value of our R is less than 1. So a lot of our proofs are going to be talking about what's the number we care about, why do we care about it, and then what's our conclusion. Since this absolute value of R is less than 1, we converge by what test? The geometric series test. So just like MVT, IVT, L'Hopital, we're going to name a test here. Throughout this unit, we're going to collect, I think it's like 8 or 9 different tests. And then towards the end, the fun part, kind of like our integration techniques chapter, the fun part is choosing. So we have to figure out which test is going to be the best. No, because this one doesn't have nearly as much like nitty-gritty math, but the choices are here. All right, so let's see if we can follow through on the next one. So it's already written like a geometric series, right? So first thing I did was identify R. What do you think R is in this one? Why do I care? All right, the absolute value of R is greater than or equal to 1. If you just wrote greater than, that's probably fine, but I like to use the definition. All right, what is our conclusion? Diverges. And I'm going to say by the geometric series test. So again, I really just want to point out the converges or diverges. If you can decide that, that's really not that cool. The cool part is the argument. So if I just see converges and diverges, super, but you're going to get like 0 points. All right. One of these I can find the sum for. Which one can I find the sum for? The one that diverges? The one that converges. So here I can find the sum of the one that converges. Now I want to find the first term to put on top. Very common mistake, saying the first term of this series is 3. Is the first term of this series 3?
No.
No, because I put n equals 1 at the bottom. So make sure you plug whatever that is. What is the first term? 1.5 or 3 halves. So 3 times a half. 1 minus my common ratio, which we already identified as 1/2. So this is 3 halves on the top, 1/2 on the bottom. So I'm going to multiply by the reciprocal. Hey, remember that one that looked like it converged to 3? It does. We did it. All right, most of the time, this is the stuff that we're going to do. Now, geometric series happen to be one of kind of 2 series we're going to talk about where we can actually find a sum. Most of the time, we're just going to be able to be like, hey, you can get one, or hey, you can't. So geometric series have a couple of cool ways we can play around with this a over 1 minus r formula. Here's one that's straight off of the AP test. Let's see if we can figure it out. So we've got a geometric series. We know that the terms are all positive. So we are given the information that our ratio is not negative. We're not alternating signs here. We know all of our stuff is positive. They've told us the first term is 108. The third term is 12. I want to know the value of this. When they say the value of this, they're saying, what's the sum of this series? So I know I need to do a over 1 minus r. Do I know either a or r yet? I know a. A is the first term, so what number is a? 108. I would like you, with your neighbors, to try to figure out what is r. It may be helpful to try to figure out what you think a sub 2 is in the process. Try to find me r. What number do I multiply by each time to get the next term? I'm going to walk around for a little bit. Usually our r's are fractions. Does that help? You can think of if you multiply or divided by a number each time. Yeah, I did. I kind of did that. All right, if you got it and you're feeling spiky, find me the sum. All right, anyone think they know what the ratio is? What do you mean 3? Oh, a third. Okay. How did you find that? Cool. All right, guess and check. That's a valid method. Did anyone find out how to get from 108 down to 12? Yeah, you multiply by a 9th or divide by 9. So to get there in 2 steps, you could multiply by a third each time. Or you could just guess and check, whatever you want. What was that a sub 2, just to check? 36. All right, so we're doing 1 minus a third was our common ratio. If I multiply that all out, 162 is our sum. All right, for my last 5 minutes, I just want to play with a couple of different questions, trying to find the sum if it exists. We're going to just look at what does this look like if I list my terms or if I have sigma notation. We're going to focus a little bit on D because that's a popular multiple choice. After I do A through D, we are done and you get to just work on your problem solving. All right, so first we're going to try to figure out, does it converge, does it diverge, it being the series. Then if we can, we're going to find the sum. So we've got first term is 3, common ratio is 2/5. We know it's geometric. Does it converge? Yes. How do you know? All right. The absolute value of r, which is 2/5, is less than 1. So this does converge. Sum. Let's just set up the fraction. What's the first term? 3. 1 minus what number? 2/5. Done. We can simplify it. Great. All right. What does it look like the common ratio in B is going to be? This one's a little bit weird. Does it help if I write 1/5 as 2/10? And this as 2√2/20. And then this as 4/40. No? All right, I multiply by √2 on the top and 2 on the bottom. Yeah, it does. It is look like a unit circle number. All right, this R, I can absolutely value it if I want. Is that bigger than or less than 1? It definitely is less than 1. So does this converge or diverge? Converge. Sum. What number goes on top? What? Square root of 2/5. That's our first term. 1 minus what? √2/2. That one's a little crazy. Easy way to do that if you want. You could take 2 successive terms and divide them. So 1/5 divided by square root of 2/5. That's 1/√2, which is the same thing as square root of 2/2. If it's hard. What is the ratio here? Rationalize. What?
Oh.
Ratio 5/4. Why do I care? Ooh, it's greater than or equal to 1. So we diverge. So what's the sum? Yeah, there isn't one. So don't tell me a sum if it diverges. Yeah. The 5. Because it's also stuck inside here. So there's also infinitely many 5s as we keep rolling through our terms. So there was that 3 in the top. Are you thinking the comparison with the 3? Yeah, so notice this 3, I was able to move out to the front because it wasn't part of that n power. This 5 is part of that power, so I can't move him. Good comparison, though. Do you guys see what Austin's talking about? All right, last one, and then I'll shut up. This one looks crazy, right? I could list out some terms, but I want to show you some cool algebra. And I'm going to lose time. All right, ready? Would you agree that 2 to the 2n is the same thing as 2 squared to the n? Because I would multiply those exponents. All right. Would you agree in the bottom? How do I get addition in the exponents? Times 5 to the power of 2. Let's collect everything that has an n power. I have a 5 in the bottom. What's 2 squared in the top? All right. What didn't I use yet? Yeah, this 5 squared in the bottom. Does that look more like a geometric series? Yeah, we'll practice with that more. What's the R? Why do I care? So what do we need? What do we know about this guy? Yeah. 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 That's fine. We'll practice both. All right. What's our first term? So first term, we're going to plug in n equals 1. So we can go anywhere we want, but we'll get 4/25 times 5 if you're using the last one. So 125. And 1 minus your common ratio, which we found was 4/5. We will definitely practice one like this again. You will definitely have one like this on probably both my test and the AP test. So we'll see that makes sense. That is totally fine. All right, so I promised I would shut up. I am shutting up now. You guys have the rest of class to work on your Unit 7 problem set. A reminder of dates, that problem set is due next class. I will again, I know. I will again give you a 30-minute block of time though. So we're gonna start class. Next class's notes are even shorter than these. So I'm gonna give you 30 minutes at the front end of next block to finish up that problem set. It'll be due after that 30 minutes. Then we'll take some notes. The assessment on this is 2 classes from now. Reminder, that is partner, and you'll have the ability to check your work. I'll be rotating around to check on notation and stuff like that. Yes. Okay. Bathroom, yes.
If I hadn't given you that verbal line, you would have had.
Yeah, I was.
We're gonna do the problem set.
I can try. That's right. If I could, Gary, you're going to have a number in the answer if you want anyone that don't say non-calculating. You could plug in, I would just plug this in. I can use it.
We have like Fox.
As long as it doesn't say non-cal. Great practice stuff. Yeah. Sorry. They think you're getting a negative number.
Yeah, but then
I know exactly what you're number. Which function, if we're looking at this like U shape, that you probably look at thing, which function is this top? So these are, so you're right, if you get exactly the negative version of this, you can get a fixed order, you can either check it or get up here, or turn this into a plus. If you want So this right here, so you're not bounded by this, that's also here, or bounded by one of the like three graphs you have, you want to take a around the area. Then you can see all the right. If that means you have that.
I'm not here.
Told you one day.
Why?
We brag about it.
Yeah, but they don't look at the bounds, that's the area. Or it's great. I mean, it's just- I was like, start walking like this, which is 1/2.
Right. I like I am now stop playing it.
I would not have.
I've never, it was like,
Yeah, that's why I think really most of them.
And you know, when I printed them, I knew that, and I was rushing. So that was like, yeah, when I do the ones with colors, I can just do them all within like, myself. It takes a second. So then, it's fine, I'll just do them all So the regret is definitely there. I got 14.
All right. Speaking of browsers, I should probably remake my Instagram when I want it. I have over the years made a lot of different problem sets, so I kind of go through my old ones and old test reviews and see what problems I like. AP Classroom has a bunch of problems too. If I'm feeling gutsy, I make my own.
All the videos are posted if you want to see it. Honestly, I find that one of it was one of the hardest units for design. I learned my space for auditing. So I need to post looking at them, working, sometimes really making It's the problem. Oh, if you guys are bad at reading directions, you can use a calculator on anything that doesn't say. I think, is there not one? Maybe I'm looking at the chart. The problem for like Gary, like my Gary.
That's tragic.
Oh, it's like, yeah, it's bad. Like, when we're neighbors in the crossway, we fight with each other and start laughing. It's like, they just knew what to do. It's funny and stuff. Yeah.
That should be fine.
It was like borderline impossible.
Oh, you're up here now.
Yeah, sorry, I got it.
What are you?
We were talking about the Gov quiz again, and how much it's like.
What was it on?
It was on.
Oh, wait.
Okay, your government makes enough sense.
Is it
Yeah.
how?
There's like 80 things that don't do anything.
Okay. To be fair, our government